So sorry about that. Forgot to record. So test will cover say applications of mass moment, um, belt drive, simple harmonic, and what is this called again? I'm missing this thing. Simple harmonic, belt drives. Yeah, those three sections, but of course you go into both applications already. Okay. To start things off, Mr. Raman had a question for me on WhatsApp regarding the belt thickness and velocity, right? So let's quickly want to address that thing. And the essential question is, should you actually introduce the thickness of the belt when calculating the velocity? So what I just want to show you is this. So just give me a second. I'm sure you guys can all hear me.
Yes, sir.
Okay, fantastic. So it's oh, just give me a second here. I just want to find this example. Quickly. So yeah, this example in your in the extra examples I sent you. What just essentially is important that they're looking for the centrifugal force um, on this belt, right? But not to show you when you're calculating the belt. Sorry, when you omit thickness, right? You sit with 549.87, right? I'm just making you aware. So and when you consider the thickness, when you consider the thickness, you're getting. Oh, okay, this is not really nicely put, but just bear with me here. So make it smaller, like that. So okay, let me just get my pen here for you guys. Right. So so the actual thing what I'm just gonna say is that, so when we include thickness, we omit, meaning we don't use it, we get this value, and when we do include it, we get that value. And this is our belt thickness of around 4.5, right? So that's quite thin actually. But I do want to make you aware that I will not penalize you, and maybe just for the semester, and it's not a big deal to me, if you don't include the thickness. But I just want to show you in terms of percent over here, in terms of percent, the impact of it. So I'm say 567.8 minus 549.87 and 549.87. So if you work on that in terms of percentage, you can see how increase by the other thickness. So in summary, I'm not going to penalize you if you. So this is around 3.2% increase. So that's quite small, but of course it means something. But the idea is that I think what I'm telling to say that I won't penalize you if you don't include the thickness. If you include the thickness, perfectly fine. If you don't include the thickness, perfectly fine. Either or, it's okay. But in normal conditions, when you are going to be checking it, you can include the thickness. It's just that some of the problems in the book doesn't have thickness, so I didn't want to like essentially confuse you. But normally, if you are presented the thickness, you can use it. It's perfectly fine with me. Your answers will still be fairly close enough. Does it answer your question, Mr. Romanus? And students, do you guys get that?
Yes. Yes, sir. It makes sense.
Yeah. Okay, yeah. So, but of course, the belt gets a bit thicker, it's going to increase. But I'm just letting you know, I'm not going to penalize you either or. But if you have the thickness, just use it. Um, it's okay with me. So we got that question sorted out. Then let's move on. But are you guys finding belt drives anyway? You guys enjoying it?
It's not so bad.
It's definitely not, yeah. All right. So next one is belt with slip. So we've been discussing, we're assuming slip doesn't happen. But now the question is, what happens to the belt when it slips, right? And this is very important. So in your textbook, on page G20, this is a very important problem. So this is what happens when the belt slips. So I'm going to prepare this on my whiteboard, and then we're going to start solving it. So let's see what they're trying to teach us here. Just going to copy this guy quickly. See what they say. Right though. So like I said, for the first session, we're going to be doing belts, and then we'll start on breaks immediately afterwards. All right, so let's get a read on this. So zoom this in. Am I sharing this? Okay, great. So an open flat belt drive connects two pulleys, 1,200 and 500 mounted diameter mounted on a 3.6 meters of on a parallel shaft 3.6 apart, right? So this is a sketch. We've got one, we've got another one, and we've got our belt going over them. I have a quick question for my students. If the diameters of the pulley are the same, what is the angle of lap?
90
If the
degrees.
diameters, no, no,
No, it's
no.
180.
Fantastic. Thank you. If you don't know why, go figure it out. Just letting you know. I'm just throwing it in there. Okay. So we've got that's 3.6 meters apart. That's what we said. Of course, sketches are compulsory. This guy is spinning at a speed of 1,200 revs. Oh, the 1,200, which is the driver. So this is the driver pulley. So we assume it's going this way. So you have T1 here, maybe T2 there. Right. Am I right about that? You guys are not saying anything.
No.
Am I right? Exactly. Yes.
So
Good.
if it's going clockwise, T1 is at the top.
Yeah. Actually was going clockwise. So guys, please sometimes I do make mistakes deliberately, and sometimes I do make mistakes just as per normal. So I'm just making okay. And then anyway, this is the main part of the question here, right? So it says, carry on. The mass per unit length of the belt is 0.9 kilograms per meter, and the tension is limited to 2 kilograms. So can this be fairly familiar with? They're saying the 1,200 pulley, which is the driver, runs at 200 revs. Sorry, and that's a mistake, actual mistake. Due to slip, very important. One of the pulleys, on one of the pulleys, the velocity of the driven shaft is now 450. Calculate torque on each shaft, the power transmitted, and the power loss to friction. What is the friction in the drive? So my question is due to slip, right? And it's giving you another RPM. What do you think? What do you think happens when the belt slips? What do you normally know about belt drives? What is common between the two things, and what happens? Well, what do you think happens when they slip? Come on, students, you can do this.
So if it slips, you're going to lose velocity. You're not going to have the same velocity on either of them. Or the same acceleration. Velocity.
Beautiful. We're getting close. So if let's just all we call this 1 and 2, pulley 1 and 2. So normally V1 equals V2, right? You agree with me? Are we on the same? Do you agree with that?
Yes.
But now you slip. V1 does not equal to V2. So in essence, part of Matthew's answer was kind of right, but yeah, you lose velocity. So it is actually right here. So remember the students, when you see the word due to slip, you know what to do. Okay, let's go. Let's start the formula analysis. Okay, so looking for the power, right? So we're gonna have to find the power of each side now, basically. So of course, the first thing we do is, in this case, the angle of lap. We have to use a smaller pulley. Let's see where the slip will occur here. Slip occurs here. So the angle of lap is smaller. Obviously, my handwriting is disastrous. Slip occurs at the smaller pulley. Where angle of lap. So I got a question for you. Now that you're more mature, why does it slip at the smallest angle of lap? You can give me an idea.
Less contact area and less friction.
Oh, beautiful, beautiful, guys! You make me so proud. I don't know. Is it the coffee I said you must drink? Really, I am so proud. Slack tension, no. Less contact area, yeah. Definitely less contact area. Remember, there's a friction drive. Less friction. Now we could say that. I like that. Essentially, what it means is that the belt is covering more on this side compared to that side. So obviously, okay. Anyway, so what do we do now? How do we find our angles? Our angle of lap is pi over 2. You say arc, right? Arc cos. So do this with me here. R1 minus R2. So we have 600 minus 250. Maybe I should adjust my thickness here. Okay. All cos, what's it? 600 minus 250. Divide this guy by 3600. Beautiful. If you get that answer, you should get 84.4. Then you have to multiply the guy by 2. It's 168.8. And of course, we work in radians for this, and we get 2,94. 2,4946 rads. Okay, that's simple enough. Now we need to work out because okay, so let me show you where we're going over here. We're gonna need to work out the power transmitted by each thing. So you know power, power equals T1 minus T2, right, times velocity. So because we have different velocities, so we have to work with velocity 1, so it's power 1, T1 minus T2, velocity 2, right? So we need to get all of that going over there. So to find out tensions, obviously, we gotta use our T1 minus Tc T2 minus Tc, and this will be equal to, for a flat belt drive, E mu theta. Okay, something popped up here. Sir, do you remind me to trust that you must do a voice question? Yeah, so remind me towards the end, right? Towards the end of our session. Thank you. Is Ms. Ramasodi here? Morning, Pauline. Morning, Tommy. Morning, Mr. Zuma. Good morning, Mr. Silva. Mr. Marat, good morning. Big chief, that guy, Mr. Marat. Taking studies very seriously. Okay. So you're limited to 2000. And of course, now we can calculate Mr. Dr. Raman's favorite parameter, the centrifugal tension. The TC is equals to mass times velocity. Easy to remember, just think of rho times velocity, rotational hoop stress. That's what I remember. We've got a mass of 0.9. We times this guy by the velocity. So of course, we know one velocity. And the velocity on the one side there for VB, right? And that's going to be, this is a quite strange part about this question, but we have to figure it out, discuss it. So it's 4,000. Oh no, it's cool. So it's for TC1, it's pi times d, which is 1.2 times it spins at 200 divided by 60 squared. Can I get that answer, please? And then we need TC2, which is also 0.9, pi times 0.5 times, let's spin at 450. Smaller one should spin faster, divided by 60 squared. Well, I think that's what I would have done. It looks a bit strange what they did. Anyway, let's see what we get here, guys. Okay, let me just erase this over here. What do we get? Here's my notes. Oh. Come on, man. Yep, there we are. Okay. So bear with me here. I'm busy tackling the idea of how this thing is done. So 142.1, right? Okay. 142.1, and the second one, newtons. Can we even do that? Do we have enough information on the smaller side? Sorry about that. I'm just getting my other note out here. All right. 142.124. 124.912. Okay. So now, what I find strange about this particular problem is that we have two centrifugal tensions, right? So what do you think we should do now? Just looking at something here. Just want to make sure. So what happens in this case here, we use the highest one within our calculations here, right? That's what we're going to do. Yeah, we use the high velocity. Alternatively, we can get the average, but we can just use the highest one. Now, this is the problem with these books. They don't actually say that. So we just find the highest one. You can actually play around and exactly see what we get. So we just use the higher one, just so that you know. For this one, let's just say it's a very important problem. There's a lot of these small things that comes out. And then we can go to our normal model to model the systems, the belt type systems for the tensions. And we get our beautiful equation. And of course, what we're just looking for here is T2. So let's quickly just get this in order. Just to get this, let's just put this in terms of T2. So E mu that, T2 minus T1, T1 minus Tc. So divide that out. So T2 is basically going to be T1 plus T1 minus Tc divided E mu. Right? That's what we get. Am I right? Divide that plus that. I think I might, yeah, I think I might. Whoop. This is Tc, sorry. That's Tc. Okay. So all we've got to do is plug and play over here. Let's see what T2 is. Tc is now 142.2 plus T1 was 2000 minus 142.2. E, our coefficient of friction was given to you, 0.3. So if you have a notepad in front of you, it's page G20. And then times, we've got it as 2,946. And therefore, we're able to get our tension in our second, what do you call this? Second, on a slack side, sorry. Okay, so what is the tension? Can someone just compute the tension for me? Beautiful. So 909,861. Yep, Mr. Mzam, thank you very much. Okay, so now that we've got our tensions, we can find our powers. Is it not so? Oh, sorry, our torque or our power. So let's see what happens. Okay, so just bear with me here. So we say P1 is going to be T1 minus T2 times V1, right? So T1 was 2000, if I'm right, minus T2, that's going to be 142. No, yes, 142. No, so it's 909 minus 909.865. That's Newton's, right? Oh, so it's T1 minus T2, and don't forget D over 2. So D over 2 to make a torque, then times that. Okay. Then once we have this guy, we have to times by D over 2. So on P1, it's 0.6. So that's 1.2 divided by 2. Obviously, this is now force times radius. And of course, now we can just times by the velocity now. Right? Alternatively, we could have done, obviously, we could have done pi equals just 2 pi nt over 60. Same thing, all the same guys. So for our velocity now, we say pi times 1.2 times that the speed is rotating by, and it is rotating at 200 revs. Let me divide this guy by 60, right? Okay. Let's get our first power. So you can see we're going to find both powers now and see what we get. So this over here, so one is the driver, right? This is the driver pulley, and that's the question is the power transmitted and the power loss to friction, right? Okay, so we'll discuss that now. So this is get one.
Sorry, sir.
Yes.
The D over 2 part of the power formula.
Mr. Kiefer, please, man. Please.
The formula is otherwise because D over 2 times velocity gives you omega.
Yeah, sorry, you're right. You're right. I'm tripping. Yes, this is what I was thinking. Yes, thank you. But no, I'm right. Wait. Just bear with me. Oh, sorry, I'm right. Sorry, man. I made a mistake here. Yep. Thank you, sirs. Thank you. I was thinking something else now. Okay. Yeah, there we go. We sorted now. Okay. Thank you very much. So let's get the first power. So the first power we should get I don't know what. Let's just quickly see. Yeah, that's LP1, and you should get 13.7 if I'm correct. Kilowatts, right? Around there. Yeah, that's 13.7. Let's find LP2. So same thing again. I'm not gonna write T1, T2, the actual values, but this is gonna be pi times our diameter is now 500 or 0.5, sorry. Spin that 450 over 60. What do we get there? So step back and look at the analysis now in terms of what are the results. We're doing the analysis, but what are our results? So do you get the answer? 12,84. 12,84 met thumbs aan. Can we agree on that one? You said 12,84. I'm happy with that. Okay. Students, are we all on the same page before I move on? Because now I like to just this is really giving me headache this thing. Anyway. Okay, right, 12,84. Students, are we all? Can I get a few thumbs up before I step back and discuss how we should look at this? I mean, this is really headache. I don't know what like this anymore. Trying to be too much. Okay, yes. Can I get two more? Mr. Doyle, go for it. Okay, so Mr. Doyle, I think Mr. Doyle has a question here.
Yeah, I know.
Okay.
I was looking for the thumbs up button.
Oh, sweet. So, if we're stepping back, right, pulley one was the one which was the driver pulley. Right? So, that would have been what our motor was giving us, right, spinning this particular system. So let me get this all right here. Where's my picture now? Okay. Got it. Just looking at this over here. Yeah, well, ours is converse, so just forgive me on the dimensions here. I couldn't find the real one. So here, because we want to transmit this to another shaft here, right? So this is 13.7 kilowatts. But due to the slippage on the one side, we're only getting 12.84 kilowatts. So this is what you kind of need to understand. So this obviously this drive is not 100% efficient. If it was 100% efficient, it would have exactly gotten 13.7 on the other end. Does it make sense to everyone? If it was 100% efficient. In this case, but due to slip, we lost some velocity as Mr. Doe stated. So what we do now, it's a fairly simple thing. So we know what efficiency is. And efficiency is a very important parameter, students, as an engineer. If you're able to find out your inputs or your outputs, and you get efficiency and you're finding a value below, of course, what your desired value, it will always indicate to you where you can actually improve on in terms of engineering systems. So efficiency is a very important metric, actually. So we can say power in or power out, right? But what's important now is that the slip, you lost to the slip, you lost energy to the slip, which you also can call as energy loss due to friction, right? So slip is energy loss due to friction. So we know, also you've seen this before probably, so P in will be equal to P out plus P loss, right? Or P friction, right? So then P in will be 13.7, and your P out in this case is going to be 12.84, and therefore that's how you can calculate our P loss. You'll see this similar concept in electrotech when we get there. So if you get your P loss, you should get 8.64 kilowatts, I think, right? That's your P loss, right? That's your power loss to friction. Power loss to friction. P loss, this is power loss to friction. So we found that one of the questions was to find the power loss to friction. Okay, so we've got that. So now just find the efficient drive. So does that make sense to everyone? How I got that? Are we all happy? Okay, and then of course to compute the efficiency, let's just quickly get it. What's P in? Of course, it must be a higher value, 13.7, and we have 12.84. So what's the efficiency of my drive? Can we get that? Hello? Is there any questions, guys?
%93.8%.
Oh, fantastic. Thank you, Nelson. So we're all happy with this. Are we all okay? Yeah, 7.3. That's fine. 7.3. That looks legit. Okay, guys. So any questions with this? If you don't have any questions, we can move on now. Do you find this interesting? Was it a nice exercise? What do you guys think? Hello? So, Mr. Mzam, why is the power loss? I'm not sure about the answer if it's right. Why do you say that? Okay, anyway, let's move on. So I'll stop sharing this. Oh, oh yes, sorry. Yeah, it's 0 point. Yeah, it's correct. Yeah, sorry. That's me. That's 0.86. Yeah, that just failed me. Of course, sorry. Yeah, that's fine. That's 0.86. Okay. Of course, it cannot be so high because otherwise. All right, guys. So just to conclude the section now, it's nothing extra. But let's start with V belt drives. Okay. So let's read here, just to give you some backdrop on where it all comes from. So it says in the past, V belt drives are made of leather. We did discuss some materials of belt drives. That, yep, rubber, canvas, or palata was previously made from leather. Then, so this is on your introductory page on around page G5. Nevertheless, okay. So, which is relatively strong and light, weighs well and does not deteriorate when subjected to high temperatures, mineral oils, and other chemicals. And the coefficient between lead and a cast iron or steel is approximately 0.3, which, although not high, but when combined with factors outlined above and the readily availability and the low cost of material made, it is the obvious choice. So, of course, because 0.3 is not a particular high coefficient of friction, but like I said, in comparison to all the other traits like being it's strong and light, it weighs well, doesn't deteriorate when subjected to high temperatures. It's fairly fine. It's a good cost-effective belt to transmit power. However, the main disadvantage of leather belts is that in order to make it strong enough to withstand tensions needed when transmitting large quantities of power, so we're talking about in the megawatt range maybe, they must be made thick and wider. However, the tensile stress in the leather is limited to a value of stress times area. Imagine, imagine if I showed you guys this before, it wouldn't make a lot of sense. So that's why I left this particular part later, so you have a bit of experience and to see the importance of what's happening here. Nevertheless, so to increase the force, the area must be made larger, obviously, right? Thus, the mass per unit length of the belt is increased. Of course, if you have a heavier belt, then this adversely affects the performance and increases the centrifugal tension. And you've obviously seen as wherever the belt is, you're going to have a bigger TC force on the belt, right? Because of this phenomenon, the speed at which the leather belts operate is only limited to around 30 meters per second. So it's interesting if you're using a leather belt, a typical flat plate or cross belt arrangement, you can only really get around 30 meters per second, right? And how many kilometers per hour is that? We're probably more familiar with that. That's around 100 odd kilometers per hour. Okay, so next, based on all of this, this is where now V belts began to gain acceptance as a viable alternative, right? So I'm saying despite the advantage inherent in them, they are more difficult to construct, being made from, I'm not sure what that is. The why can't I see that? Yeah, they made largely from rubber. So I think they are sensitive to high temperature mineral oils, right? And the V groove pulleys are more expensive to manufacture, obviously, than flat belts. And also, as well, we shall see the V shape is a factor by which the coefficient of friction is multiplied. That's increasing the ratio of the tight side to the slack side tension. Okay. The last part basically says here. So modern technology has made it possible to produce flat belts made of synthetic materials, which are extremely light and strong. You can operate up to 100. So we don't anymore use leather anymore. So we have this new synthetic type material. So, and that's basically that's before the centrifugal becomes a problem. It is interesting to note that the leather is still used as a friction material, a thin layer being laminated inside of the belt, right? And therefore it's now possible to transport over 1 megawatts, a single belt. That's fantastic. So the only way to transmit large amounts of power with a V-belt drive is to have a number of belts running in parallel. That's a multi-groove pulley is necessary. So this arrangement has the disadvantage that some belts stretch more than others, but there's no way of tensioning the belts. So just to look at the differences between flat and V-belts. So in these drives, the pulley has a V-shaped groove machine and it's in its perimeter, right? So so just to look at it, that's what it looks like. You get to this. It's grooved to the V. And the V-belt or the rope drive. So by the way, when we're doing V-belt drives, we also do exactly the same analysis for rope drive. So rope drive is just a circular belt over there, right? Oh, my okay, sort it out. Nevertheless, and there's of course so the V-belt or rope drive effectively increases the coefficient of friction, thus permitting more power to be transmitted. Remember, this is a friction drive, not a positive drive, right? So let's look at some comparison. Flat belt drives are good for moderate transmission and with the distance between the shafts is large, so that's cool. For V-belts, high power transmission and the difference when the shaft is small. I'm sure you guys seen that. Also, there's a chance of slip due to less frictional grip between pulley and belt. Hence, it's not a positive drive, yes. And then on the V-belt side, there's a less chance of slippage, basically. Flat belts require large space, obviously. That's consequently it's good for large distances. And of course, V-belt requires less space due to compactness. So with flat belt drives, you get high velocities. V-belt, less, high velocity ratio between the drive and the driven. So that is for the V-belt, that's highest, it's less for the flat. And basically for the same value of the coefficient of friction, the angle of contact and the allowed tension, the power transmission of the belt is less than. So basically a V-belt can transmit more power depending relative to the coefficient of friction, angle of contact, and the level of tension. So basically we do exactly the same analysis as before, and all we end up with is this new model, and the model is essentially, so it's still T1 minus TC over T2 minus TC equals E mu theta cos is, what is it, beta, right? Am I right? So now that's the only difference between the two. So what is this new beta, right? Let's quickly discuss. So the beta is called the groove angle. So it says this applies to all belt and rope drives. A flat pulley is equivalent to a V groove pulley for the included angle of 180 degrees. Thus 2 beta equals 180 and beta equals 90. In essence, what's most important of all of this is that we have a new groove angle essentially. The groove angle is this over here. And what we need to do when we have a groove angle, when we do our calculations, we have to divide the groove angle by 2. So you'd pick that up within the calculation. So it's also fairly simple, just an extra add-on. Okay, so based on this, into an example, see how this all works, right? Students, are you all there? Students?
Yes, sir. We are here.
Yes.
Fantastic. Okay. Don't know what happened to my whiteboard
yeah.
now. Sticking in. Yeah, thank you. Just give me a second. Why is it doing this now? It's loading. Okay, so we just have probably this one, or there's another example I can do. No, this is the wrong one. This is the one I'm doing. Oh, I don't know if this is the wrong one. So this should be example of, here we go, example 5. Okay, great. It's done. So it's all essentially the same. It's nothing really just adding an extra thing within the okay, I'm assuming it's shared now. There we go. So let's read this question. So the drive or motor to a machine shaft by means of a single open V belt, right? The shafts on the motor and machine are parallel and 1 meter apart. The motor pulley A has a diameter of 150 and turns at the revs of 1,600, while the machine pulley B rotates at 400. The allowable tensile stress in the belt is limited to 8 megapascals. There's a density of 1,900 and a cross-sectional area of 800. The coefficient of friction is 0.13. It is between the pulley and the belt, and included groove angle is 34 degrees. How much power can the belt transmit? So all we need to do is go basically our formula again. If you remember, what's T1 minus TC, 1 minus 1 over E mu theta cosec times velocity, right? That's what we need to do. Simple. Just got cosec theta. Okay. So let me just make a whiteboard bigger here. So first thing is first, right? Because there's no slip, our velocities are equal, and we end up with our ratio of NA. So the reason why I'm doing this is so that we can find our let me just go to the note quickly so we can find obviously our contact angle. Here's my notes. Give me a second, I'll paste that for us. So we have a picture. All drives. Example 5. Got it. So sketch there. So that's what we're dealing with. And so what we can do, we need to obviously find the angle of contact on the smaller pulley. So we could obviously find V1 or find velocity of the one and then just work backwards, but we know that pi d n over 60, so I'm going to call that n1, d1, and pi, I've done this for you before to show you what it is, d2, n2 over 60, that and that will cancel, that and that will cancel, d1 times n1 equals d2 times n2. So we needed the diameter of the other one. So we have for the motor pulley, we have 150 at 1,600 revs. So it's 150 times 150 times 1,600. That's that guy, the smaller one, and then we need the other one, and that's going to be only given us 400 over here. So we have to find D1. So of course, the answer is given here, but in this case, so I'm just making you aware, in this case, we need to find the diameter of the other one. Okay? So let's do that. So it's 150 times 1,600 divided by 400, and you'll get 600 millimeters. So if they don't give you the diameter, remember this. Sometimes you're going to have to find it yourself. Likewise with the rotational speed. So don't forget that. And of course, we're assuming no slip here. It's on the first assumptions. So then it's an open flat. So pi over 2 is cos -1. We're going to say 300 minus 75 divided by the center distance of 1,000 is 1 meter. All right. And we should get an angle of, what is our angle there? Of theta. What would theta be? Just get that quickly. You get 76.997 times that by 2. You should get 153.99 degrees. We can just call it 154. Thank you. And of course, convert that guy into radians now, and we should get 2.688 radians. Right. Next thing, what we can do is find our centrifugal tension. So we've got our mass per unit, do we? No. So we have to find our mass, and our mass times velocity. But of course, in this case, we have to say density times area times velocity. So we're always working per meter in this case. So that's 1,900 times 800 to the power of -6. That'll give us our mass, and our velocity is going to be the same. So we just use the one that we know. That's going to be pi times 0.15 times 1,600 divided by 60. 1,600 squared. And let me just get a centrifugal tension for me. It's a very nice problem, very nice one. What did you guys get for that one? You guys get the answer. It should be 177 newtons. You guys happy with that? Let me see. Nope, I got a different answer. Let me just check. Oh, the density is wrong. It says, oh, they use a different density here. That's why. Okay, so 240. You guys get that?
Yes, sir.
Yeah.
Okay, there we go. So T1 is stress times area. So we lump it to 8 megapascals. We times it by the area. It's given to us, fortunately. And then we get a value of 6,400. So that's the maximum That will be the tight side, right? Then all we need to do now is go back to our power formula. T1 is 6,000 minus TC is 240.03. We can say 1 minus, now E minus, one if you guys knew this, it's the same as this, just easy to work with. Just bring this guy to the top, cosec beta. So with a groove angle, what we do now, we keep this in degrees. That's one thing I cannot answer you why, but for us to get it right, that must be in degrees, right? So coefficient of friction is going to be at 0.13. Angle of lap is still 2,688. And our groove angle, right? What I tell you, if you see a groove angle, the included groove angle, you have to divide by 2, and therefore it will become 17. So groove angle, always divide by 2, the included groove angle. So it's just a plug and play thing here. So, but keep it in degrees as well, right? Cosec 17. And then a velocity, you can use either one, obviously, but if you've calculated the velocity, you should have gotten 12.57 over here. So can you guys calculate the power for me? And see, are you guys able to get this? I'm waiting for a specific question. So what is the power, guys? And of course, this is negative, sorry, negative. So if you're going to do it in a calculator, so I guess no one is saying anything, so I was asking, you're going to have to say 1 over sine of 17. That is cosec over there. This cosec is not on your calculator. So what power do you get? Hundred and 19. Ooh. That is not the same ones in the book. Do we make a mistake somewhere? Oh, that's 6,400 here. That's the first thing. It's still awfully high though. What is this centrifugal tension is 107? Yeah, 53 should be, 53,996. Thank you, Tommy. That looks right here. Around 50, let's call it 54 kilowatts. Yeah. That looks good, yeah. It's a lot of power being transmitted there. Fantastic. Okay, guys, so what's essentially important is when you have a rope, drive, or weave up, you just have to adjust this and just basically know in terms of the groove angle, you have to divide it by 2. So I like to end belt drives. I'll give you an example to do. Go to your textbook. So I'll just quickly stop sharing this. because we reached the end of the first session. Go to your textbook. There's an example. Treat it as as page G19. There's a small tutorial for you. We've got the answers there. So what's just important to note, because we're going to go on a small break, then you'll continue with belt drives, is that now we have 2 V belts in parallel. So what it means essentially, you're going to work for each belt, you're going to work per belt, and then and then basically you have to multiply by the exact amount. So go on this page, attempt this problem without looking at the solution. And what's also important here, what I did mention to you, 2 parallel pulleys, 2 parallel of the same size, and the pulleys are the same size. Your angle of lap is 180 degrees or pi radians, so 3,14 radians. So anyway, guys, you made it to the end of belt drive. Let's try this one. Let's reconvene at 10:30. Our lecture today will end. What time do our lectures end today? Our session anyway. By 1:30, right? Am I correct?
Yes, sir. 1:20.
Okay, 20 past, yeah. So anyway, have a nice break. Just to, but if you wanna, I recommend doing this example just to keep yourself going. So on G19, and I'll see you at 10:30 to start on brakes. See you then.